in exercise 12C, you're going to actually just be graphing. So you're graphing the log function or some variation of the log function. So the basic log graph is this red shape here, and most log graphs end up being a variation of that. So it might slide up or down, it might become a little bit steeper, it might shift sideways, but basically you get this shape. Now, you could probably, so some features of it are, it is a positive, it always has a positive gradient, it's always increasing. It doesn't exist for negative x values, and the reason being because we can't find the power to raise a number to give us a negative value. And remember the x, we're taking the log of x, so x is the number that we are producing after raising the base e to a power. It has an asymptote in the negative y-axis, so it's actually going down here, getting closer and closer, and never cuts it. It doesn't have a turning point, no turning points. And if you think about the derivative, if we've got y is equal to the log of x, then we know that y dash is equal to 1 on x. Can 1 on x ever be equal to 0? No, 1 on x can never be equal to 0. Therefore, there are no turning points. That's not to say that if the graph of y equals log of x plus x squared or something like that, that could have a turning point, because then we're adding more to this function. But just be careful that, yes, our, just think about the log graph and I guess its basic shape. Now, you will be required for the first couple of times you draw a graph of a log function that you fill out a table of values, and to do that you'll simply use your calculator. So you're focusing on this key here, the log key. I'm not sure why I erased that. We want 0.5, close the bracket, and equals, and you can see it's this negative 0.69314, blah, blah. We're not going to be able to graph to that accuracy. You would, however, call it probably negative 0.7. Of course, the log of 1 is 0, because what do you raise e to? What power do you raise e to get 1? Raise it to 0 power, so at x is 1, we've got 0. And I would actually always identify that x-intercept on your graph, just because it's standard practice to identify intercepts if they're easily if you can identify them easily. So put them on your actual graph. And you can see that I've just used the calculator to fill out the rest of those values. Log 10 being approximately 2.3, so put that in. They have been graphed. You don't very often see a scale on this y-axis. You actually probably, the only real value you see here on the x-axis also is the intercept. And just, if you were graphing this, just be careful. At 2, it's 0.7, 3, 4, 5, but then we jump to 8, so we're actually graphing here at x is 3, x is 4, x is 5, jumping to 8, and then jumping to 10, and you get that graph. Now, after you have done that, you could probably just think about the impact of the putting a negative in front of all your values, and you could probably see that you get a reflection in the y-axis, which you are familiar with. You've seen that before. So, sorry, not the y-axis, a reflection in the x-axis. So we would get a graph that had been way up here, and it cuts, and then it comes down and it travels along similarly down here in the negative values, and it runs on up there, and the positive y-axis becomes an asymptote. So that's this one. Y is the log of x plus 2. Well, like it's saying here, remember your transformation. What does adding 2 do to the graph? It actually pushes it back 2 units. So we would need to extend our x-axis along here. We put in -1 because the graph's going to move back 2 units. So you're going to have this exact shape, and there'll be an asymptote at -2. So the graph will come up from 1, and when x is 0, it'll be the same as at 2, which was 0.7. So it's going to cut across here, and then go along, and so that's this one. Log of x plus 2, this plus 2 is different to that plus 2, note the difference, pushes the graph up, so we now have something like this. So when x is 1, we're up here, and I'm not sure, you possibly could identify this x value. We've basically got the same shape happening again. So you can see there that I'm solving log of x plus 2. Where is that equal to 0? So log of x plus 2 equal to 0. Where is log of x equal to -2? Using the definition of a log, the log of x is the power to which e needs to be raised to get x. So we know the power is -2. So then I went to the calculator and did e to the -2, and it's saying that the number is 0.13, whatever. So we'll say approximately 0.1. So this x value here, and maybe it would be best to call it e to the -2. Sketching the log of x and the log of x all squared on the same number plane actually gives a very interesting looking graph. You know y equals log of x, but then think about log of x all squared. If you're squaring it, what do you know? You know you can't get a negative number, so where your regular, the red log graph here, is negative, it becomes positive. So you'll probably end up with some combination of this and maybe a bit steeper, and then this. A little bit steeper because it's square. I'll leave that one for you to actually do. And again, just choose some values. Obviously you'll be choosing some values between 0 and 1. Don't choose 0, but do a half for x, etc., and square it and see what the answer you get. And you can draw those graphs, and then you're right to do 12C.